These are Kinetics Moodle Quiz 5 sample problems. And before we begin, let's revisit our equations note card. And if you need, you can pause the video and jot these down. And if you have a first order reaction, you will want to use these equations. This one's the half-life equation. These two are the same equation, just derivatives of one another. And then this is your second order equations, and that's the half-life equation. So number one, we have a second order reaction where A goes to products, and it has a rate constant K of 1.4 times 10 to the negative 4, an initial concentration of 0.079 molar. What is the concentration at time 352.0 seconds? So first of all, we notice it's a second order reaction, and so I want to look at my second order equations. It does not mention half-life anywhere in the problem, so I don't need this equation. I only need this one. So what I'm trying to solve for is the concentration of A at time 352 seconds. So I'm going to go ahead and move this to the other side by adding 1 over A0 to each side of the equation. And this will leave me with 1 over the concentration of A is equal to K times T plus 1 over the concentration of A0. So now we can plug in our values. K is 1.4 times 10 to the negative 4 times 352.0 seconds. And all of this will be plus 1 over the initial concentration, which is 0.079. And so let's see what we get when we plug this into our calculator. 1.4 times 10 to the negative 4 times 352 plus 1 divided by 0.079 equals. So we're going to get 12.7. However, we have to be careful because this is equal to 1 over the concentration. And so I'm actually going to have to take the inverse of each side of this equation in order to get my concentration of A. So I'll type it to the negative 1, and we get 0.07869 molar is the concentration, which is letter A. Number 2, sodium 24 is a radioactive isotope with a half-life of 14.8 days. So we have a T1/2 equal to 14.8 days. Radioactive decay is a first-order process, so this is first order. How many half-lives are required for a sample of sodium-24 to decay to 1/64th its initial concentration? So really we just need to know if I had a whole amount of sodium-24, how many times does it cut in half before it becomes 1/64th its initial concentration? Well, if I cut it in half one time, I'll have half as much. Cut that in half, I'll have 1/4. Cut that in half, I'll have 1/8. Cut that in half, I'll have 1/16. Cut that in half, 1/32. And cut that in half, I'll have 1/64th. So we have to divide 1 by half 1, 2, 3, 4, 5, 6 times in order to reach a concentration 1/64th of what it was originally, which is letter A. Number 5, iodine 131 is a radioactive isotope. Radioactive decay is a first order reaction. So first order. The initial concentration of iodine 131 is, so this is A0, is 0.1712 molar. After a time of 48 hours, the concentration, so the new concentration, becomes 0.1439 molar. What is the half-life in days? So first of all, they want the half-life in days, but the time we were given was in hours, so we should go ahead and convert hours to days. And of course, 48 hours is equal to 2 days. So because it's first order, let's look at our equations. And essentially, we're going to have to use both the half-life equation as well as one of these two. It really doesn't matter which one. Since we were given both these two concentrations, I'll go ahead and use this equation. Because I want to end up with the half-life, we're going to end using this equation here. And what I need before I can use this equation is the rate constant k. And so I'm going to solve this equation for the rate constant k, and then I can plug that into this equation in order to get the half-life. So we'll take the natural log of the concentration of A is 0.1439 divided by the initial concentration, 0.1712, is equal to negative K times 2 days. And so I'll go ahead and divide both sides by negative 2, and what that'll give me is K equals, put it in our calculator, the natural log of 0.1439 divided by 0.1712, close parenthesis, and all that is divided by 2. Sorry, negative 2. We get a K of 0.08686, and now I can plug that into my half-life equation. The T1 half equals the natural log of 2 divided by this value of K. So I will now take the natural log of 2, close parenthesis, divided by the previous answer, and that's going to give me a half-life equal to 7.98 days, or based on the answer choices we're given, we'll round that off to 8 days, which is letter D. The following plot was made for the natural log of the concentration of reactant A as a function of time for a first-order reaction. So it's a first-order reaction. This is number 6, by the way. From the information in this graph, determine the half-life. So what is T1 half? And remember, because it's a first-order reaction, we're going to need this equation for half-life. Half-life equals the natural log of 2 over K. And what I need to know if I want to use this equation is, what is K? Well, if you are familiar with how the graphs work, then we can determine K by looking at the graph. So here's a reminder that when you have a first-order graph, the slope is going to be equal to negative K. And so because we are given a negative 0.15, then K is equal to 0.15, because we just want K, not negative K. And so I'll take the natural log of 2 and divide by 0.15, and that's going to give me 4.621 seconds, which is letter D. Reaction take, we're on number 7. Number 7, a reaction takes place and the concentration of reactant is measured at various points in time. Here are the observations. At time 0, the initial concentration is going to be equal to 4.5 molar. So I'm going to jot that down. A0 equals 4.5 molar. At time 15 seconds, the concentration of reactant is 1.8 molar. A plot of the natural log of A over A0 versus time gives a straight line. So if we look back at our graphs, if you have the natural log of the concentration over the initial concentration, if that gives you the straight line, then that indicates to us that we have a first order reaction. And so first order equations will be used to solve this problem. A plot of 1 over A versus time does not give a straight line, and so that indicates that it's not second order. What is the concentration of the reactant at 3.4 seconds? So time equals 3.4 seconds. What is the concentration of A at that time? Here's the equation that we're going to use. Notice that I'm missing two things. I don't know the final concentration, but I also don't know K, and so I have too many variables. So what I can do is I can use the information at time 0 and at time 15 seconds in order to find K first, what is the rate constant of this reaction. Then I can do a second calculation with this equation where I use that rate constant in order to solve for the concentration of A. So the first step is going to be to plug in these values. So the natural log of 1.8 molar minus the natural log of 4.5 molar equals negative K is what I'm trying to solve for at time 15 seconds. And so when we do this math, we get a K equal to 0.061. Now I can take this K and use it in this equation to solve for the concentration of A. I'm going to use the natural log of the initial concentration, 4.5 again, equals negative 0.061 times, and the time we're solving for this time is 3.4 seconds. I'm going to add natural log of 4.5 to both sides of the equation and do this math so far. So I have negative 0.061 times 3.4 plus the natural log of 4.5, close that parenthesis. So we're going to get natural log of A is equal to 1.2967. However, I'm going to have to raise both sides by e in order to cancel out this natural log. And so I'll take e to the previous answer, and that'll give me 3.657 molar, which is going to be the concentration at 3.4 seconds, which is letter C.